Okay, so good morning. So I'm Mark Philo. My burger tastes like sugar. My first part is I just need to ask a quick question or raise of hands. Who doesn't know who sugar is? It doesn't matter if you put your hand up. This is actually a little test of mine to A, if you're young enough, B, maybe you're a visiting worker, or maybe it's a senility test. So Shergar, it was a famous racehorse in the 80s, and he won everything. He was great. And eventually his time was over, and he went to stud in Ireland. He was then duly kidnapped, and the owners didn't want to pay the ransom, and he went missing. So the rumour was that he actually ended up in the butchers and on people's plates. Or Shergar. Which brings us into of my talk today. So in 2013, we had the food scandal scare of the horse meat in food. This wasn't the first time it actually appeared in the UK. Just after the war, black market trade in meat actually introduced horse meat into the butchers. But in those days, it was done by maybe the look and the funny taste. But in 2013, we were armed with more scientific methods, and the way they actually detected it was by using DNA and ELISA techniques. So these techniques are still used today and are very good. They can be a little slow and they're quite expensive. So we at IFR took on a strategy grant, it's a Kickstarter project for 1 year. So we're going to look at a fast, high throughput technique for speciating animals and any adulteration. And for purposes of this project, we were concentrating on the 4 meat groups of horse, beef, pork and lamb. The principle of our method is not to actually look at the muscle tissue itself. We were targeting the myoglobin. The myoglobin is similar to hemoglobin, but the myoglobin will transport the oxygen content throughout the meat tissue itself, which is what gives it a red colour. It's a protein, so therefore it has an amino acid sequence, and there are databases where you can get the amino acid sequence. And from there we will target specific peptide regions from the protein and are analysed by LC mass spec. Sampling is actually quite simple for our method. We freeze the sample and grind it to a powder. With a form of aqueous extraction, which is very convenient because myoglobin is water soluble and will leave behind the more complex proteins which we don't want to interfere with our method. We'll then do a tryptic digest, which I'll get to in a while. All this is done in a buffer, so there's some measure of cleanup before it's allowed to go to the LC mass. So this is a little more complicated now. I'll concentrate on my horse and my cow. So these are, as we get from the scientific databases, and you'll see that they are basically a set of amino acids, which each letter corresponds to the list of amino acids there. And as you can see, as later on we'll be using a mass spec, each amino acid has its own mass. So just to clean it up a little bit, comparing my cow and my horse myoglobin protein, by initial look they actually look very similar. But now in closer inspection you'll see that there are some amino acid differences between the two, even though they're similar, and it's these differences of course which we're going to target to speciate the myoglobin types. So just move on to my horse only. This is my myoglobin protein, which I have now aqueous extraction. The next stage is to do my trypsin digest, so it's an enzyme digest where it actually cuts between the lysine and the arginine amino acids in the protein. So this will break up the protein into now my peptides, which I now going to start targeting. And some of the peptides are rather small, so I can't really do anything with. But there are some significant protein strands which I can then target to take to my mass spec. So just lining them up between my horse and my cow now. There are more peptide strands, but I've just selected a few. So we can see we've got a few peptide strands from their individual myoglobin proteins. We've coined the phrase CPCPs, which is corresponding protein, being the myoglobin, and corresponding peptides, which is the peptide from the same region of the myoglobin protein. And you can see at the top I've actually got two peptides which are actually identical. So in this case, this peptide is shared between these two animals and actually several other species. So this is common between them. But once we get into the differences of particular amino acids from the same area, we do actually get differences in mass because of the differences between the two species. And this is what I'm going to be capitalising on for my mass spectrometry. So the mass spec that I use is here, and so I do HPLC separation using here my data pointer to separate the peptides chromatographically, and then the mass spec will isolate the mass of the peptide. But being a triple quad, it actually goes a bit further than that, and it actually breaks up the peptide that I have isolated into fragments, and then I analyse the mass fragments of that. That actually gives me greater selectivity and sensitivity to that peptide so I can identify it. So this is what the mass spectrometer sees. So here I have my chromatography. Anybody who does chromatography, actually, this gives me great chromatography. It's the best I've actually worked with. So the B is beef and H is horse. So here I have unique peptides for beef and a couple that are common to beef and horse. Correspondingly, I have my 100% horse. And here I have a common peptide, again, for beef and horse, but I have unique ones to the horse. So that's nice, I can tell the difference between the two. We went a bit further to look at adulteration in meat. Our target was to get to at least 1% of adulteration. And here I do have, we ground up some horse into beef at 99% beef, 1% horse. So of course my signal is going to be dominated by beef, being 99%, and I can just see my horse signals here. But of course I can tell my mass spectrometer to only look for horse. So when I clean it up a little bit, I get an excellent, very strong signal to show me that I have horse. So we're very encouraged that we can see, even at a 1% level, we get very good detection for the adulteration of horse in beef. My talk today is incredibly well timed, fortunately. The Kickstarter project was a novel technique to bring through, and we were able to submit it to analytical chemistry. We only learned this week that it's been fully submitted, and as of last night is available online. So perfect timing. So this is the picture of our title page, and it's an excellent time also to name the crew who are on the title of the publication, being Andrew Watson, Yvonne Gunning, Neil Rubin, myself, and Kate Hensley. So what's coming next? We're coming to the end of the year on our one-year grant, and with the success of what we've had, we're actually moving on for a further 2-year study where we're gaining some industrial input financially. So we're going to look at quantification of adulterated myoglobins in meat. We're going to look at smart digestion kits. So these are new on the market and promise to speed up the whole sample preparation so we can do much higher throughput in a 96 well plate format. We're going to look at processed foods, so such as lasagnas and salamis, etc. And in fact, we have already had a little look at this, and I'm pleased to say that the limited number of processed foods we have taken from the local area all are actually the meats that stay on the packet. And we're going to expand into some different meats. So when you're in a restaurant and you may choose your various meats for consumption, we'll just check that they are indeed the meats that you're eating. You may have a taste for more obscure meats. And in fact, only yesterday I read a story of a steakhouse in Watford that was selling zebra meat, turned out to be horse meat, and wildebeest, turned out to be cow, which is now no longer on the market. But with adulteration, you may well find some meats that you don't wish to be on your plate. And with that, I'll ask you to dine on your lovely cake today, and I'm sure that the ingredients are as advertised. Thank you.